Hello again, guys. Today I'm gonna keep solving some examples from chapter 5, and this is the one that I selected for the first one. Let's read the problem. It says the member AB is supported by a cable BC. So we have this member here, AB, and it's supported by a cable BC. And at A, this point, by the square rod, that's important, which fits loosely, that's also important, through the square hole at the end joint of the member as shown. Determine the components of reaction at A and the tension in the cable needed to hold a 100-pound cylinder. So the first thing that we have to do is figure this thing out and doing like a free body diagram of what is happening. Let's start with whatever we have as data, whatever is given to us. We know, as it says there, that this is a square rod, and it says that it fits loosely also. What else do we know? We know the coordinates of this cable, coordinates for B and C, which is going to allow us to calculate this or express it in vector notation. We know also the weight of the cylinder is 80 pounds. And now we have this type of support here. Okay, the important thing is recognizing what are the reactions that are going to be acting here. Let's start with the tension, because the tension is the easiest one. Tension always goes in the direction of the element, like that. And this is going to be tension B or tension BC or force BC. The weight of the cylinder is going to be acting here, which is 800 pounds. And then we have to check the type of reactions that this support is producing. Well, let's start from the force reactions. This structure is held by this square rod here. So at point A, that rod is preventing the movement in the direction Z. That's why we are going to put a reaction at Z. And this is going to be called AC. I'm going to use this because AZ. What about the X direction? Well, in the X direction, because it says that it fits loosely, basically these could slide through that element, meaning there is no reaction happening in this axis. Now, what about in this other direction? Well, in this other direction, which is the direction Y, yes, we're going to have also a reaction in the direction Y. And I think it's obvious, that reaction. So we have this AZ, and we have this AY, and we have this tension. Now, regarding the moments, the way this is built and designed, if this wasn't a square bar, that could rotate freely around this point, but because the bar is a square and this is the other pin that is happening here around the hand, and because this is a square, then this is gonna be stuck over there. Basically, what I'm trying to tell is that there is gonna be a moment generated around the y-axis, around the x-axis, I'm sorry, like that, due to that connection there. And you know, there's a way of connecting the moments or expressing the moments with double arrow, which is easier sometimes to visualize than the curved arrow for the direction wise. Now, in this other direction also, because this part is like that, it can't rotate in this direction around this point. So there's going to be also a moment produced here around Z. And there's going to be a moment acting there around that Z. This is going to be MX at A. This is going to be MZ, MA at Z. this one. And what about y? Y is this one. Well, of course, you have also a moment about y, which is going to be acting here in this direction. Not here, it's here, but I'm going to express it like that. And it's going to be acting, I'm going to put it positive for now. This is going to be MAY. So basically, how many reactions do we have? We have 6 reactions. No, not 6, 5. Y5, we have AZ as force and AY. Those are 2 forces because AX doesn't exist. And then we have 3 moments. MAY, MAX, and MAZ. Now, what are we asked here to do? We have to calculate the reactions at A and the tension BC. And how are we going to proceed? Remember that you can use either Cartesian notation or you can use a scalar formulation. I'm going to solve this problem with a scalar. A scalar equations of equilibrium. That's what we're going to do here. I'm going to use a scalar equation of equilibrium. You can solve it by using Cartesian notation and compare afterwards. Okay, let's start in that way. Let's do that. The first thing that I'm gonna do here is express or calculate the components of this tension, because even if I'm gonna work with Cartesian notation, I need the components in the different axes of this TBC. And how are we going to do that? Well, remember, we can say that TBC as a vector is going to be the magnitude of TBC multiplied by the unit vector, dot multiplied by the unit vector in the direction of BC. This is nothing new. We have been doing that forever, so we should be really like an expert doing that, or I hope so, that you are an expert doing expressing vectors as with the magnitude and the unit vector. The first thing that we need for the unit vector is getting the position vector and dividing that position vector from the magnitude. What is the position vector? Position vector BZ. Well, if I have to go from this point to this point, basically I'm gonna go in the x direction 3. I'm gonna go in the y direction -6, and I'm gonna go up +2 in the k direction. But this is just the position vector. That position vector, remember, has to be divided by the magnitude of the position vector, which is the square root of 3 squared plus 6 squared plus 2 squared. And that, at the same time, if I multiply that by TBC as a magnitude, that's going to give me whatever the vector TBC is, or the force TBC is. So the vector TBC as a vector is going to be, this is 9, 36, 49, square root of 49 is 7. So it's going to be TBC that multiplies 3/7 in the I direction, -6/7 in the J direction, plus 2/7 in the K direction. And remember, from time to time, it doesn't hurt to put the units for that. Okay, now once I have that force, the other force, of course this force is going to be going in the z direction negative because it's the weight acting like that. So we can start applying our equations of equilibrium. The first one that we're going to do is summation of forces in x equals 0. So if we do summation of forces in x equals 0, in this direction, there is no force in x, and there is nothing else in x. What do we have in x here? There's nothing. We have no reaction here, so I'm not going to copy anything, and we have this component of the force. So basically we have 3/7 of TBC equals 0 because there's nothing else applied there. There's nothing else resisting it. Then TBC is 0. Look how easy you got the first unknown here. Now if we do summation of forces in Y equals 0, then let's see what do we have in Y. Y is this direction. So in direction Y I have AY. Yes, AY. And I have the J component, which is negative 6, 7 of TBC. And I don't have anything else equals 0, but we just say that TBC is 0, so that means also that AY is 0. And now summation of forces in Z equals 0. Now let's say what we have in Z. We have AZ negative 800, which is the weight, and plus 27 TBC. You don't have to copy this every time. I'm just putting it that we know is 0 equals 0. And then from here I have that AZ is equal to 800. Okay, now the only part that we are missing is MAX, and we are missing MAZ and MAY, the other three unknowns. Let's do that part. Let's do summation of moments then. I'm gonna start doing in this part here, and I'm gonna start with summation of moments around Z equals 0. Around Z, I have of course MAZ, which is this moment here. Do not confuse this with force, because I have the moment, which is this, and I have two arrows in that drawing. So MAZ, and whatever this force was going to produce around Z. But because this force is 0, then MAZ doesn't have any other thing to do there, so it's 0 also. Now let's do summation of moments about X. X is this rotation, and in this rotation, I'm having MAX, which I copy positive, not like that, like that. This is the direction, okay? The arrows is the direction of MAX. Actually, this should be acting in this way to make the drawing clear, more clear. So MAX is in this direction, and what else do we have in X? This force of 800. If this is like that, this is the point like that, and I apply the force at this point, and this is pulling it down, this is causing the element to rotate about the x-axis, which is this one, and it's going to cause an inward rotation, and if it points in this direction, it's going to be negative 800 multiplied by 6, which means that, and I don't have anything else because this force, I'm not going to keep complicating my equation, this is 0. So MAX is going to be 4,800 pounds-feet, or MAX could be also 4.8 kip feet. My last but not least of the unknowns is summation of moments with respect to Y equals 0. And by doing that, I'm going to have MAY this is coming from below, that's why it looks like it's coming in this direction. It looks like it was in that direction, but it's coming from below. That's what I prefer the double arrow to show the sign. So MAY, what else? Does this force produce anything about the y-axis? No, because this and this, the only rotation that it's going to produce is about the x-axis, and this is 0. So MAY is also 0. This is a typical example of a problem that looks super complicated, and it's super easy, because if you realize this is 0, this is 0, this is 0, this is 0, and basically the only one that we have a value for that is MAX. I think I'm missing something here. Yes, no, maybe. I had the reactions, let me see. AY, AZ, 1, 2, 3, 4, no, that's it. I have everything there. Okay, that's it for this problem, and I'm gonna solve the new one in the next video.